In this video, we'll look at nuclear fission. Now, in the previous video, we talked about nuclear fusion, the combining of light atomic nuclei into heavier nuclei, which then releases energy. And your book shows a plot up here on the right-hand side, showing the binding energy, if you will, of each atomic nucleus. And you can see on the left-hand part of the plot, near hydrogen, the bonding energy is low. For helium and so on. It peaks at around iron and then slowly descends as you get heavier than iron. What this means is iron is the most tightly bound nucleus. To the left of this plot, if you combine lighter nuclei and you get closer to iron, you undergo nuclear fusion. On the right-hand side of this plot, you have heavier nuclei that you can break up to release energy to get to iron. So iron is basically the most stable nucleus. Nuclear fusion occurs in massive stars much more massive than our sun, until iron is produced. Once iron is produced, the star actually very quickly, about a day or so, blows up into what's called a supernova, because you cannot fuse iron and release energy. Neither can you fission iron and release energy. Either process, if you break up an iron nucleus, it takes energy. If you combine an iron nucleus with something, it takes energy. So iron is the most stable nucleus. So elements heavier than iron, usually much heavier than iron, when you break them up, you actually release energy. This process is called nuclear fission. So a heavy atomic nucleus is broken up. In the example here, uranium-235 can spontaneously break up into daughter products, in this case xenon and strontium, and release also free neutrons that fly off into space, or the surrounding material. So heavy elements, there are isotopes of heavy elements, and some heavy elements like uranium are all radioactive. They will all spontaneously decay into lighter nuclei. How long this takes depends on their half-life. For uranium, that half-life can be billions of years, or for certain isotopes, it can be a few seconds, depending on which isotope you're talking about. Now, spontaneous fission occurs, like in the example above, uranium-235, uranium-238 can spontaneously break down. Radon gas in your basements in Wisconsin, radon gas is a big problem. Radon is radioactive and does decay and release daughter cells. That's why it's dangerous gas to have. It is, on the right-hand side of the periodic table, a noble gas, a non-reactive gas like neon and helium. But radon itself, while it doesn't chemically react with much, it is a radioactive isotope and can decay, and that radioactivity, if you breathe in radon gas and that radon gas decays in your lungs, it can damage the tissue and cells in your lungs, causing cancer. So that's why you don't want radon gas building up in your basement. Now, this spontaneous fission, while it does release energy, this spontaneous fission is actually what keeps the Earth hot. The Earth should have cooled off long ago. It formed over 4.5 billion years ago, but its core is still molten. Largely, it has a solid iron core, but the molten iron core around that and the mantle is still heated. It's heated by the radioactive decay of heavy elements in the crust. However, for nuclear fuel, you can't just you might pick up a rock that contains uranium and might notice that it's warm in your hand. But a warm rock, and that of course is damaging your hand, the cells in your hand as your hand is absorbing that energy, that warm rock isn't really a good power source. So, to make a power source for nuclear reactors or bombs, you need to do something extra. You need to find an element, or find an isotope that you can induce to break up. Uranium-235 will spontaneously decay, but you can't hurry that up normally. I mean, you can't just will it to decay faster, but you can set up a situation where you can force it to decay. And this is called neutron-induced fission. By sending a neutron into a heavy nucleus, and again, this is just a placeholder for any real heavy nucleus, you can, depending on the isotope, cause a fission reaction to occur where two daughter cells typically, daughter nuclei are created, not cells, two daughter elements or isotopes are created, and neutrons are released. So you can induce a fission event. That is useful when generating power. That is useful when creating a bomb, right? To induce energy to be released very rapidly. An example of that would be sending a neutron into uranium-235. Now, 235 uranium, the nucleus has 92, or it's uranium, right? So it has 92 protons. So trying to fire a proton at it is tough because those 92 protons repel in the nucleus that one proton you're trying to send in. But neutrons are neutral. So sending a neutron into uranium-235 temporarily makes it uranium-236, which is highly unstable and decays very quickly into many different sets of daughter products. For example here, barium and krypton. And then 3 neutrons are released. Now those 3 neutrons can go, and if they interact with nearby uranium-235, they can cause reactions, which split out, each of those 3 reactions splits up more neutrons. Now you have 9 neutrons. And each of those reactions splits up more neutrons. Now you have 27 neutrons, and so on. Those neutrons sometimes hit, or most likely either fly out of the material, or are absorbed by, let's say, uranium-238, and are trapped. Uranium-238 becomes uranium-239, which isn't highly radioactive. It doesn't immediately decay, and that neutron is lost. So how do you create a situation where you can get what's called a chain reaction, where you have a huge amount of uranium, you start this process, and these neutrons go off to create more fusion prospects and so on. You want this chain reaction to occur. In a bomb, you want it to occur explosively, where each of those neutrons goes to create a new fission event, and the neutrons created there create a new fission event, and the bomb explodes. But for a reactor, of course, you don't want it to explode. You want your fuel to remain producing energy, but at a stable rate. So look at that next. Now, while uranium-235 is an excellent nuclear fuel to use in atomic bombs and in nuclear power plants, a couple of downsides, of course. The daughter products, are usually themselves highly radioactive, potentially for thousands or hundreds of thousands of years. So unlike the dangerous byproduct of nuclear fusion in the PP chain, which is helium, which helium has a lot of industrial applications, cooling supermagnets and so on, the daughter products of nuclear fission are usually deadly and unwanted. So it's nuclear waste. And where do you put this nuclear waste? That's a problem that the US and other countries with nuclear power have had to deal with. There was a facility called Yucatan Mountain in Nevada, an old copper or salt mine, I forget which, where they were going to store the nuclear waste from the various power plants, nuclear power plants in the US. But while they built the facility, then lawsuits prevented actual use of the facility. So currently, I believe the nuclear power plants have to store their own fuel or own nuclear waste on site. So Nuclear-235 is a great fuel. Uranium-238 and other uranium isotopes, they're not just 2, there are many, many different uranium isotopes. Uranium-236, 237, 238, 239, 240, etc. And below. You want uranium-235. That's the fuel. That's the isotope of uranium that is useful as a fuel. So how do you get it? Well, you take a big chunk of uranium, as much as you can get, and you have to purify it. You have to get rid of the isotopes you don't want and keep the isotopes you do. To do that, you have to enrich your source for uranium-235. A popular way to do that is using centrifuges, gas centrifuges. So you basically vaporize your sample, spin it up at a very high speed. Uranium-238, which is heavier because it contains more neutrons than uranium-235, is pulled out. the uranium separates. You get rid of the uranium you don't want, you keep the uranium you do, and you enrich it this way. It is a slow process. And how enriched you make the fuel depends on how useful it is. You want the fuel, you can't enrich it too much because pure uranium-235 will basically explode on its own. So you have to figure out what percentage uranium you want it to be enriched to, and whether or not you're going to use it in a bomb, in which case you want it to be enriched at a higher percentage so it's easier to detonate, or for nuclear fuel, in which case you don't have to have it. You don't want it enriched too much because you don't want your nuclear reactor to turn into a bomb. So, what a nuclear reactor using this fuel is self-sustaining in that the reaction is, you've got this chain reaction going and the reaction is stable. Enough neutrons are being produced that for every reaction you have with uranium-235, a neutron goes off and also reacts uranium-235. But remember, for every uranium-235 split, 3 neutrons come out. Those 3 neutrons could potentially create a chain reaction. So you want to absorb the extra neutrons somehow. And to do that, you usually use neutron-absorbing rods. They're physical rods that are put into the fuel, into the power plant, to absorb the excess neutrons. If you absorb too many neutrons, the reaction slows and eventually stops. If you don't absorb enough neutrons, then the reaction builds and builds and builds and can eventually explode. So what you want is to have a reactor at critical. Now this goes against probably every sci-fi show or disaster movie you've seen where people yell out, the reactor's about to go critical. It's supposed to. The reactor needs to be at criticality in order to sustain the reaction. What you don't want is a reactor to go supercritical, which sounds even worse. It sounds like made up. Oh no, the reactor's not going critical, it's going supercritical. Well, actually, yes, supercritical is bad. It would basically mean the reactor is going to melt down. It's going to potentially explode. So, we want a situation where you have the reactor at criticality, self-sustaining reaction, enough neutrons being produced to keep the reaction going, not too few that the reaction stops, and not too many that you get a meltdown. Now, uranium-235 is not the only nuclear fuel that's used. Another popular nuclear fuel is plutonium. A breeder reactor is a special type of reactor, creates plutonium from uranium-238. So you can take the uranium-238 you removed in your previous step and actually create plutonium with it in this breeder reactor. Plutonium, like uranium-235, is easy to fission. And so you can use this plutonium to produce energy. And in fact, many of the NASA probes that go to other worlds far from the sun, where solar energy is weaker, actually use plutonium as a heat source. They're not a nuclear reactor. So the Curiosity rover, which is about as big as a small car, a very small car, driving around on Mars right now, actually has plutonium in it that produces heat, and then electricity is generated off the heat created by the plutonium, the decaying plutonium. A lot of deep NASA probes have plutonium as an energy source. NASA is actually running out of plutonium because the US hasn't really built a new nuclear reactor in decades, and hasn't really built many nuclear bombs in decades. So there's no new plutonium being produced in the US. So NASA has actually had to ask the Department of Energy to create plutonium that they can then use for their distant spacecraft. And I have mixed feelings about that. I love space exploration, but plutonium is a rather nasty substance. So I'm unsure of where I stand on that right now. So this is nuclear fission. So nuclear fission deals with, again, this is the power source. We talk about a nuclear reactor in the US or abroad. This is how they're generating energy, through the division of heavy nuclei into lighter nuclei.